right. All right, so today is lecture number 23 of Math and Modeling Methods. Lecture number 23, which means that after today we only have 2 lectures left for the semester. That will be a lecture next Tuesday before we break for Thanksgiving, and then a lecture when we come back from Thanksgiving, Tuesday of that week. There will be no lecture on Thursday because we have the exam, the in-class version of the exam. That would be Thursday, the 3rd of December. And then we have a take-home version of the exam, which you'll return to me on the following Monday. Okay, so you'll have that weekend to work on that exam. Okay, are there any questions? I posted the homework assignment. Have you had a chance to check it out? It's on Canvas. It's a few problems that you have to answer analytically, and a few problems that you have to use some of the spreadsheets that I posted to be able to get a numerical answer. Or you can come up with your own spreadsheet, or you can, again, you're free to use whatever language or mathematical spreadsheet you prefer. All right, so from now until the end of the semester, which is basically 3 lectures, we are going to be concentrating on partial differential equations, and coordinate frames are different than the Cartesian system. Okay, so we're going to be looking at cylindrical coordinate system, see how the diffusion equation and the wave equation look like in the cylindrical coordinate system and on the spherical coordinate system, and how the separation of variable works if we have those equations looking differently, and if it actually applies directly or if we need to do anything special. So essentially what we'll do in the next 3 lectures is purely analytical. Okay, we will not, although the finite differencing techniques that we've covered can be applied directly to problems in other coordinate frames, they're usually reserved to be applied in Cartesian coordinates. And even if you have a geometry that looks cylindrical or that looks spherical, then you can break that geometry into Cartesian planes or into Cartesian coordinates or grids. So the methodology applies exactly the same. There are some body-fitted mapping techniques where you can take Cartesian geometry, non-Cartesian geometries, and turn them into Cartesian geometries. But that's obviously beyond the scope of this class. So separation of variables in cylindrical coordinates. And we'll see that, let's start with the case of the diffusion equation. Which is the one that we've been mostly dealing with. And the diffusion equation, remember, we have Laplace. In this case, it's a heat diffusion or energy diffusion equation. It's the Laplace of the temperature, but now the temperature is in R, theta, Z, and T. It's still a 4-dimensional function, but now instead of x, y, z, we're framing it into another reference plane or reference system, R, theta, Z, and time. And obviously we have the same time derivative on the right. So the equation looks identical, there's no difference. However, the operator, the Laplace operator, as you know, in cylindrical coordinate system, is slightly different. And we went over these in the first section of the semester when we studied field theory. All these vector operators, we started with the gradient and divergency, then we noticed the divergency of the gradient is called the Laplace, and these take on different forms in different coordinate systems. So, in particular, in cylindrical coordinates, this looks like ddr, r dt dr, plus 1 over r squared, d second t, d theta squared, plus d second t, dz squared, is equal to 1 over alpha dt dt. Okay, so notice that the operator takes on a slightly different form. We have those r's embedded into the operator. Obviously, in the radial direction looks completely different than the x direction. The tangential direction has that r squared because of the arc length in the denominator. And those are the metrics of the transformation that we cover in much detail in the beginning of the semester. The z-coordinate actually looks identical to the z-coordinate in the Cartesian plane or the Cartesian system because it is the same coordinate essentially. It is the same reference. So now we're essentially looking at a cylinder or cylindrical system, and if we can embed that into the Cartesian coordinate system, basically that cylinder, it's that cylinder is the actual direction of that cylinder is the z-axis, and the center above the z-axis, so it's the axis of revolution. Any point on the surface of the cylinder by a position vector r has a coordinate z. And when we project it onto the xy plane, as an angle theta with respect to the x-axis. Now, in terms of separation of variables, assume that all boundary conditions at r, theta, and z are homogeneous, and that the initial condition is non-homogeneous. Okay? If that's the case, separation of variables should apply. This satisfies all the requirements of separation of variables. First, the geometry needs to be framed in the orthogonal coordinate frame, and despite the fact that this is not a rectangle or a cube or a box, it is still orthogonal. Theta is orthogonal to z, and z is orthogonal to r, and therefore theta is orthogonal to r. The geometry is framed, the boundary conditions are all homogeneous, the initial condition is non-homogeneous, and therefore separation of variables should apply directly without any superposition required. And I'm going to say here, it should apply directly. Alright, so when we have multidimensional problems like this, what do? We say let temperature, which is a function of r, theta, c, and time, be equal to, first, let's make this a function of space and a function of time. Function of space and a function of time. Standard separation of variables. Then we worry about separating w into r, theta, and c. So the governing equation becomes Laplace of w of r, theta, and z divided by w of r, theta, and z is equal to 1 over alpha tau prime of t divided by tau of t. And because the left and the right have different dependencies, the left is only a function of r, theta, and z, the right is only a function of t, that cannot be, and therefore the only way that they can be equal to each other is if they're equal to a constant. We're going to make that constant as always lambda squared, and we're going to make it negative because we know this is a diffusion problem, and the diffusion problem is going to lead to a decaying exponential. Also because we want to form eigenvalue problems in the physical dimensions, r, theta, and z. Therefore, we need that minus sign. We need to form eigenvalue problems because all boundary conditions are homogeneous. The eigenvalue problem is what's going to make us find a solution that is non-trivial. It's going to allow us to find a solution that is non-trivial. So, the problem in tau, or in theta, or in t, will look like tau prime of t plus alpha lambda squared tau of t is equal to 0. And this is exactly the same problem in time we had before in Cartesian coordinates, which leads to a solution that looks like a e minus alpha lambda squared t. Standard solution of a first order linear differential equation with constant coefficient, homogeneous. All right? In the case of W, the equation we have is Laplace of W r theta z plus lambda square W r theta z is equal to 0. Remember what's the name of this equation? Laplace of the function plus the constant times the function. This is called the Helmholtz equation. This is the same equation we found in Cartesian coordinates, same one. But now we have to break it up in pieces. We're going to let W of r, theta, and z be a function of r, be a function of theta, and be a function of z. Same standard procedure that we've used before. And now let's see how that looks like when we plug it into this equation. Now remember that the Laplace looks like 1 over r d dr of r times dw dr, and in this case of r, theta, and z. In the theta direction, we have 1 over r squared, the second, the theta squared of r, theta, and z. And in the c direction, we have plus the second, the z squared of r, theta, and z, plus lambda squared times r, theta, and z is equal to 0. So this is the equation. And if we divide everything by r, theta, and z, and notice, okay, again, identify that these theta is not a function of r and z is not a function of r, therefore they can be taken out of here. R is not a function of theta, z is not a function of theta, so that can be taken out of that operator. So basically this will result in 1 over r of r times r double prime of r plus 1 over r prime of r plus 1 over r squared of theta double prime of theta divided by theta of theta plus z double prime of z divided by z of z plus lambda squared is equal to 0. Okay, that's a standard step, but now it's looking differently than the case of the Cartesian coordinates, especially in the r direction and in the theta direction. All right, so let's start by separating the z from everything else. Okay, so we'll have 1 over r times r double prime of r plus 1 over r prime of r plus 1 over r squared, theta double prime of theta, theta of theta, plus lambda squared is equal to minus z double prime of z divided by z of z. And we apply the same rationale that the things on the left are functions of r and theta, the things on the right is a function of z only, and therefore the only way that they could be equal to each other is if both are constant, and we're going to call that constant eta. And since we want to form an eigenvalue problem in the z direction, we keep that constant positive because there's already a negative sign here. Okay, so that the equation in the z direction looks like an eigenvalue problem. Z double prime plus eta squared z. All right. So now in the z direction we have z double prime of z plus eta squared z of z is equal to 0 plus homogeneous BCs. And by the way, the homogeneous BCs can be of any kind, right? Can be first kind, second kind, third kind. So we go to the table, the standard table that we have. For rectangular problems and find what are the eigenfunctions and what are the eigenvalues. So, z of z is equal to, well, it's going to look like b cosine of eta n z plus c sine of eta n z. And the b and the c, eta n, eigenvalues, and z n of z, eigenfunctions, and n of eta n, the norm. And this is from table. From table. So it's either the sines or the cosines, so the eigenvalues are either the pi, n pi over L, L being the actual length, and so on. Okay, so this is solved identically as before. All right. So now we go back to this equation and keep the start from scratch here. This is a 1 over r double prime of r plus 1 over r prime of r plus 1 over r squared theta double prime of theta of theta plus lambda squared is equal to eta n squared. Now we know that that's an eigenvalue, and therefore we put in the index n. So now let's try to, we multiply everything by r squared so that we can separate the theta here. So we have r squared over r of r double prime of r plus 1 over r prime of r, and we have plus r squared that multiplies lambda squared minus eta n squared, and that's equal to minus theta double prime theta. And now we're going to separate this. Obviously, same argument. Things on the left are functions of r, things on the right are functions of theta. This is completely separated. Then the only way this is going to be equal to each other is if they're equal to a constant. And we make that constant equal to nu square. And we make it positive because we want to form an eigenvalue problem in the theta direction. So in the theta direction, we have the equation theta double prime of theta plus nu square theta of theta is equal to 0. And now we have plus homogeneous or periodic DCs. Okay, what does that mean? If we have a full circle, remember now we're talking about the axial direction, the tangential direction, theta. If we have a full cylinder or a full circle, there's no boundaries. There's no boundaries to a circle. It wraps it on each other. So the only thing that we can say about it is that it is periodic. That the solution at any degrees, at any angle, is equal to the solution at that angle plus 360 degrees. Okay, that's the only thing that we can say. If we have a wedge of a circle, that's also a solvable problem, a wedge of a circle with a finite amount of angle, then we actually need boundary conditions at different values of theta. That would be like this. For example, well, in either case, we'll have theta of theta be equal to d cosine of nu m of theta plus E sine of nu m of theta. Okay, that's a solution. And essentially, if wedge, for example, we have something like this. Then we will need theta at theta 1, and then we'll need theta or a boundary condition at theta 2. Either first kind, second kind, or third kind. It really doesn't matter. Or if full circle, then what we'll have is that theta of theta is equal to theta of theta plus 2 pi. Periodic. Boundary conditions. So if we have a wedge, we actually have boundaries in the theta direction. If we have a full circle, we don't have boundaries. So the only thing we can say in order to eliminate some of these constants is apply periodicity. All right. So if we do have these, then we apply boundary conditions, and then we go to the table because it's the same type of solution. Depending on the type of boundary conditions, we're going to have an eigenfunction, an eigenvalue, and a norm. Okay, so this will lead again to eigenvalues, eigenfunctions, and the norm from table. All right. So now we're left with r squared over r of r double prime of r plus 1 over r prime of r, plus r squared lambda squared minus eta n squared is equal to nu m squared. So let's rearrange this, and this will be r squared, r double prime of r, plus r times r prime of r, plus r squared, where are we? Let's call this beta n squared times r squared minus nu m square R of R is equal to 0, such that beta n square is equal to lambda square minus eta n square. All right, and what's that equation? Remember? That's the Bessel equation of order nu m. And by the way, this needs plus homogeneous PCs. We need homogeneous boundary conditions in the R direction. So the R solution is equal to, remember, we are up to D, E, F, G. F times J of nu M of beta n R plus G times, what is it, Y of nu M of beta n R. If nu M is different than an integer, for F, J, nu M, beta n R plus G, J minus nu M, beta n R, if nu M is, I'm sorry, this is if it's equal to an integer and this is if different than an integer. Okay, those are the Bessel functions of the first and second kind of order nu M. So then, what do we have? The temperature of R, theta, Z, and T will be the summation from n equals 0 to infinity, the summation from m equals 0 to infinity of whatever R of R would be, whatever theta, theta we called it m or n. Theta m of theta, Zn of Z times e to the minus alpha lambda square t, and there's a constant of integration here, a and m. All right. Find a and m through orthogonality of all eigenfunctions using the initial condition. Right? And by the way, sorry, one thing. We're going to make this beta. Let's just make it beta here. And this beta is going to be, and it's going to end up being an eigenvalue. These are the zeros of these. And this is beta L, beta L, beta L, beta L. And there's another summation here. Sorry about that. From L equal n 0 to infinity. So there's three nested summations. And this is RL of R. And this is constant of integration of 3 indices. And recall that lambda squared is equal to beta L squared plus eta N squared. Okay. Now this is in general how you solve a problem in cylindrical coordinates, but obviously every one of them, depending on the combination of coordinates you have, not always you'll have all coordinates be dependent or independent. R, theta, z, and time. Sometimes you'll have a problem in R and t. Sometimes you have a steady state problem in R and theta that's called a polar coordinates problem. Sometimes you have an axisymmetric problem where theta doesn't come into play. Nothing changes in the theta direction. So every one of those cases leads to a slightly different combination of results in regards to these different eigenfunctions. So the different cases go like this. Let's say that you have problems in R and theta, and these are called polar coordinates. The governing equation looks like 1 over R ddr r dtdr of R and theta plus 1 over R squared the second t d theta squared of R and theta is equal to 0. So we're looking at a steady state problem in R and theta. Let's say boundary conditions in theta, we have a full circle. So periodic. And in R, we have t at b comma theta is equal to some t0 of theta. Right? So we have the following. So this is a circle of radius b. And on the exterior we have a first kind boundary condition, Tb of theta is equal to T0 of theta. Some given function, and I'm going to use a hat here to indicate that that's given. Alright? And it's a solid circle. It's full, so the conditions in theta are periodic, and it's solid. There's no interior diameter, radius, although they could be. Full circle. Solid, full, solid circle. If that's the case, again, there's only one non-homogeneous condition, so we technically can apply SOV directly. Let T of R and theta be equal to R of R, theta of theta. The governing equation will be 1 over R double prime of R, plus 1 over R prime of R, plus 1 over R squared, theta double prime of theta, over theta of theta, is equal to 0. Then we separate, multiply everything by R squared. R prime of R is equal to minus theta, double prime of theta, theta of theta. Again, we've managed to separate them. And now we make this lambda squared. So because we want positive, because we want eigenvalue problem in theta. We don't want an eigenvalue problem in R because the condition in R is non-homogeneous, as you can see. There's a temperature given different than 0, given a radius equal b. let's see how we deal with these conditional periodicity. So, in the theta direction, we'll have theta double prime of theta plus lambda square theta of theta is equal to 0. This will lead to a solution that looks like theta of theta is equal to A cosine of lambda theta plus B sine of lambda theta. And then we apply a periodic condition. That means that theta of theta should be equal to theta of theta plus 2 pi. We can go around a full circle and find the same solution. All right? So, what do we learn about applying this condition? What is the outcome of applying this condition to this equation? If we say theta of theta should be equal to theta of theta plus 2 pi, can we get A or B or lambda? When is that possible? When is it possible that the cosine of an angle be equal to the cosine of an angle, or the cosine of an angle times a constant is equal to the cosine of that constant times that angle plus 2 pi? Think about it. It would only be possible if the lambda is an integer. This is only possible if lambda is an integer. If lambda is a fraction, then that will not be possible. The cosine, or the sine for that matter, of a constant times an angle, it's not periodic if the constant is not 2 pi, if the constant is not an integer. So this is only possible, the periodic condition is only possible if lambda is integer. So we're going to let, therefore, lambda is equal to n, which is equal to 0, 1, all the way to infinity. So the solution theta of theta, because of periodicity, just becomes cosine of n theta plus b sine of n theta. So basically the eigenvalues, these are eigenvalues, are just integers. None of that n pi over L or anything like that. There's no L in the theta direction, just n. The eigenvalues are just integer numbers. All right, now let's look at the R equation. The R equation would look like R squared, R double prime of R, plus R prime of R, minus lambda squared R of R. By the way, that's not lambda squared anymore, because remember, this one has been turned into n squared. So let me rewrite this. All right. So what does that equation look like? Again, this is a ordinary, second order ordinary differential equation, homogeneous, variable coefficient. What does that equation look like? Is that the Bessel equation? The modified, it would be the modified because there's a minus sign. Okay? But it's not because the Bessel equation needs an R squared here. Too. So how do we call that equation that has the coefficient, polynomial coefficient decays with the order of the derivative? It's the Cauchy-Euler equation. It's the first one we looked at. Okay? Cauchy-Euler equation. Remember, the Cauchy-Euler equation is the simplest of all. when we have something that looks like that, we can try the solution R of R to the alpha. Therefore, R prime of R will be alpha times R, alpha minus 1. And therefore, R double prime of R will be alpha, alpha minus 1 times R to the alpha minus 2. And we plug it in here. R double prime times alpha, alpha minus 1 times R, alpha minus 2, plus R, alpha times R to the alpha minus 1, minus n squared times R to the alpha should be equal to 0. Notice that the R squared and the alpha minus 2, the minus 2 cancels out, so we have alpha times alpha minus 1 times R to the alpha plus R times, alpha times R to the alpha minus n squared R to the alpha is equal to 0. And now we can take the R to the alpha out as a common factor, or we can just simply cancel it out. And then we have alpha times alpha minus 1 plus alpha minus n squared is equal to 0. And that, if you keep solving, it will be alpha squared is equal to n squared. And therefore, alpha is equal to plus minus n. So the solution in the r direction is r to the n, where n is the eigenvalue in the theta direction. Right? Except, notice here, we did this Cauchy-Euler equation extensively before, but notice here that when r is equal to 0, we cannot cancel out like that because we end up with 0 over 0. Okay? So there's an exception there. So the solution will go like this. R of R, this is the general solution of the Cauchy-Euler equation, would be C times R to the n plus D times R to the minus n, or this is if n is equal to 1 through infinity, or C plus D times the log of R if n is equal to 0. All right. Now we need to apply boundary conditions. Okay, remember that the non-homogeneous boundary condition is reserved to the end. With orthogonality and all that, we can determine the constants of integration. In this case, this problem has a single condition. Okay, R has only one bound. Unlike X, Y, and Z problems where there's always two bounds on either side, in the case of R, we only have one bound. If we had a hollow circle, then we had two bounds, A and B. Okay, but we have only one. Now, can we say something about the inner bound, although it doesn't exist? The inner bound will be R equals 0, right? Although that's not a boundary, we can say that that's the lowest value that R can take, R equals 0. Can we say something about R equals 0 to cancel out one of the constants of integration right away? Or to determine them? See, at R equals 0, what is the log of 0? 1. What? Infinity, or minus infinity. The log of 0 is minus infinity. How much is 1 divided by 0 to the power of n? Infinity, right? Can we allow the temperature to be infinity? Never. It's never going to be infinity in the center of a circle or anywhere. So since temperature of R and theta, which is, remember, R of R times theta of theta, must be finite everywhere, then that's including at R equals 0, then D must be equal to 0. That's a conclusion that we always make when we have solid circles or solid cylinders. So R of R is then equal to either c r to the n or c. If n equal 1 through infinity, or if n is equal to 0. Well, that's pretty straightforward. It's the same. One is the same than the other. When n is equal to 0, r to the 0 is equal to 1. So these two are the same. Alright? Now you cannot say this if the circle is hollow. D does not vanish if circle is hollow. Alright? So when we put the solution together, which is r of r, theta of theta, this will look like a0 plus the summation from n equal 1 to infinity of an times the r to the n cosine of n theta plus bn r to the n sine of n theta. So this is the general solution. Now, apply non-homogeneous boundary condition at r equal b to find a0, an, and bn using orthogonality or through orthogonality. Okay, so that means that t at b comma theta, which is equal to some t0 hat theta, some given function of theta, is equal to a0 plus the summation from n equal 1 to infinity of an b to the n cosine of n theta plus bn b to the n sine of n theta. All right. And we're going to use orthogonality of the cosine of n theta and sine of n theta. And we're going to use it 3 times. If we integrate this directly, you're going to tell me. I'm going to integrate the left from 0 to 2 pi t0 hat theta d theta, so without multiplying by anything, is equal to a0, the integral from 0 to 2 pi of a0 d theta plus the summation, let's see if I can fit this in here, of an b to the n of the integral from 0 to 2 pi of the cosine of n theta d theta plus bn b to the n times the integral from 0 to 2 pi sine of n theta d theta. All right. What is the integral of the cosine? It's the sine, right? If we evaluate the sine at 0, what do we get? 0. And if we evaluate the sine at 2 pi, we get 0. Okay? What is the integral of the sine? The cosine. If we integrate the cosine at 0, what do we get? 1. If we integrate the cosine at 2 pi, what do we get? 1. Remember that n is an integer. Okay? So this one will 0, and this one will 0. Those two integrals always go to 0 over a full wavelength from 0 to 2 pi, over a full period. So, and what is the integral from 0 to 2 pi of a0? a0 being a constant? It's just 2 pi times A0, right? So out of these we get that A0 is equal to 1 over 2 pi times the integral from 0 to 2 pi of whatever function we're given that is the boundary condition on the periphery of the circle. Alright? Now similarly, we can take that expression here and multiply times the cosine of n pi. That will cancel out all the terms in the summation except one. Same thing we do with orthogonality. And that will mean that a sub n is equal to 1 over pi b to the n times the integral from 0 to 2 pi of t0 hat times the cosine of n theta d theta. And that bn is equal to 1 over pi b to the n times the integral from 0 to 2 pi t0 of theta sine of n theta d theta. Same principle. First, I didn't multiply times anything, just integrate it. Then I multiply times the cosine on both sides, integrate between 0 and 2 pi, and this is what I'm going to get. It's orthogonality. We've used them many times. All right. Now, in this problem, if you look at this problem, the problem is supposed to be a problem of r and theta, right? So you expect the solution to be a function of r and a function of theta. And we see that in the general solution. The general solution is indeed, looks like, a function of r and theta. R and theta, okay? Now, that's only possible because the boundary condition in a periodic problem is a function of theta. That's only possible because of that. The only thing that will make the solution change as a function of theta is the fact that this boundary condition is a function of theta. If the boundary condition that I give you is a constant, if I tell you the temperature on the periphery is 100 degrees, yes, the function will change, or the problem will change in the r direction, but it will not change in the theta direction. So somehow the theta dependency on the general solution there will cancel out. So for a problem to change in the theta direction, you have to have something to force it to change in the theta direction. In this case, well, the boundary condition that is given is changes in the theta direction. Now if we have an annulus, hollow cylinder, let's say that this is A and this is B. And again, the governing equation, let's say 1 over r d dr, r dt dr, and r and theta, plus 1 over r squared, the second t d theta squared of r and theta is equal to 0. And let's say now that the boundary conditions, remember, in order to be able to apply separation of variables, we need to have only one non-homogeneous condition. Let's say that the inner condition is 0. Again, it's first kind. There's no flux or anything. The temperature is forced in the inner cylinder or in the inner radius. And let's say that the temperature is also forced in the outer radius, but it's now forced to be some function of theta, which is given. Alright? So, again, let T of r r and theta be equal to r of r theta of theta. And that would lead to, we don't need to go through the decomposition and separation. We know that that would lead to this. Where the eigenvalues n are just integers. And we know that the r of r is going to be c r to the n minus or plus d r to the minus n if n is equal to 1 through infinity, and c plus d times the log of r if n is equal to 0. Same thing we found before. This is essentially the same problem. Periodicity. Okay. So, the general solution is going to look like C0 plus D0 times the log of R plus the summation from n equal 1 to infinity of Cn r to the n plus dn r to the minus n times a n cosine of n pi on n theta plus bn sine of n theta. Alright, so we assemble the equation and then we apply even the homogeneous boundary conditions. We say that the boundary conditions, temperature at A, comma theta, that's the inner radius. That says that C0 plus D0 log of A is equal to 0. Therefore, C0 is equal to minus D0 times the log of A. Okay, that comes from here, when n is equal to 0. This is for n equals 0. Now for n greater than 0, then we have Cn times r to the, or times a to the n plus dn times a to the minus n is equal to 0. And then we have Cn is equal to minus dn divided by a to the 2n. That's you. So now we put it back together here, and we have d0. So c0 is replaced by d0 log of a. So this will be d0 times the log of r over a plus the summation from n equal 1 to infinity times r over a to the power minus a minus r over a to the power of n times fn times the cosine of n theta plus gn times the sine of n theta. Notice that I've combined the coefficients an and bn with the remaining coefficient dn and d0. I'm sorry, dn only. So basically fn is dn times an and gn is bn times dn. So now we still have those three constants of integration to determine. Now using remaining non-homogeneous boundary condition, where t, b, and theta is equal to some function of theta that is given, plus orthogonality, results in the following. D0 is equal to 1 over 2 pi log of b over a, integral from 0 to 2 pi of f theta theta. Fn is equal to 1 over pi times b over a to the power of minus n plus b over a, minus, to the power of n, times the integral from 0 to 2 pi of f theta times the cosine of n theta d theta, and gn would be the same thing. B over a minus b over a times the integral from 0 to 2 pi f hat times the sine of n pi on theta d theta. And those are the three constants of integration found in three different shots. All right, now things can get really tricky in cylindrical coordinate system, and again, every combination of coordinates will lead to completely different solutions, and even within the same coordinates, like what we just did, if we have r and theta, it depends whether the circle is full or solid or hollow, whether we have a wedge or we have a full circle. The eigenvalues are different, the combination of functions are different, the actual solution of the Cauchy-Euler equation, or the log and the r to the minus n are preserved. Now, one of the good things about doing things in the cylindrical coordinate system is that unlike this Cartesian coordinate system, we can actually do external problems or exterior problems. And the solution would actually appear naturally. This will only be possible in Cartesian coordinates using Fourier transforms. Okay, and that's something, again, beyond the scope of this class, but you might have seen it in your undergraduate math, from Fourier transforms. But in the cylindrical coordinate system, it actually comes naturally. So let's say that we have a domain that extends to infinity, or semi-infinity, okay, so as far as the eye can see, and then we have a circular hole in it. And that circular hole is a radius a. So let's say that the governing equation again is 1 over r, ddr, r, dt, dr of r and theta. Again, this is a from an r and theta, we're not changing that. Plus 1 over r squared, the second t d theta square of r and theta is equal to 0. With boundary conditions, let's say that the temperature at a, comma theta, is equal to 1 plus the cosine of 4 theta. It is given, and it's that function. Okay, so it's what we call f hat or t hat. Now we know it. And the other thing we know is that t as r goes to infinity, n theta must be finite. However long this is, the temperature cannot go to infinity. It must exist. So we go through the same process. Again, we have a single non-homogeneous condition. Again, we let T of R and theta be equal to R of R theta of theta. And that would mean that the governing equation will look like this. Same thing we did before. Nothing changes. We're looking at a completely different problem that extends to infinity, but nothing changes. Again, the only thing that drives this problem to have a theta dependency is the fact that the boundary condition depends on theta. Otherwise, this problem would be theta independent on the entirety of the domain. So we multiply everything by r squared, r double prime of r of r, plus r prime of r of r, is equal to minus theta double prime over theta, and we make that equal to minus mu squared. So in the theta direction, remember we have theta double prime of theta plus mu squared theta of theta is equal to 0, which would lead to a solution. We've done this again. A cosine of nu theta plus B sine of nu theta. So we don't have boundary conditions, so with periodicity in theta means that theta of theta should be equal to theta of theta plus 2 pi. That means, therefore, that nu is equal to n, which is equal to 0, 1, all the way to infinity. Integer. Nu must be integer for that to be possible. So, theta of theta is equal to A cosine n theta plus B sine n theta. In the r direction, we have r squared times r double prime of r plus r prime of r minus n squared r of r is equal to 0. That's again the Cauchy-Euler equation with solution r of r equals to c r to the n plus d r to the minus n. That is for n equals 1 through infinity. And I'm going to use different constant names instead of c and d, just to do it appropriately, because they're going to be ending up being independent of each other. I'm going to call them E and F. All right. So what happens here? Let's see what cancels out. So the condition says that r, as r goes to infinity, must be equal to finite. And if that's the case, who cancels out? When r goes to infinity, how much is r to the minus n? 0, right? So this goes to 0, that's fine. How much is r to the infinity? Infinity, right? Well, I'm sorry, how much is infinity to the n, where n is a positive integer? That's infinity. So c must be 0 in this case. How about in the second one? E is a finite number, that's fine. Here, what is the log of infinity? It's infinity too, right? So then therefore f must be equal to 0. And therefore, r of r is equal to either d times r to the minus n or e. And that is for n equals 1 through infinity, for n is equal to 0. And now we have the combination here of the two solutions, the theta solution and the r solution. All we need to do is put them together into T. T of r and theta is equal to r of r, theta and theta, which is equal to A0 plus summation from n equal 1 to infinity. R to the minus n is simply 1 over r to the n. And the constants of integration, I'm just going to call it a and b, even though they're not necessarily a and b. They're a times d and a times e, but they're just another letter. I'm going to keep them as a and b. This is the general solution. Okay. Now, once we have it all together, we apply t at a and theta equals 1 plus the cosine of 4 theta. By the way, this is a given function. It's not that it's like that. It's just that we were given the fact that in that window, in that hole, on the periphery of that hole, the temperature looks like that. So, 1 plus the cosine of 4 theta is equal to A0 times summation, or plus the summation from n equal 1 to infinity of 1 over a n times a n cosine of n theta plus bn times the sine of n theta. And now we use orthogonality. A0 is equal to 1 over 2 pi times the integral from 0 to 2 pi of 1 plus the cosine of 4 theta d theta. Okay? What is the integral of the cosine? The sine. It will be the sine of 4 theta. The sine of 4 theta at 0 is 0. The sine of 4 theta at 2 pi is the sine of 8 pi. The sine of 8 pi is also 0. The only one that survives here is a 1. The integral of 1 is 2 pi. 2 pi divided by 2 pi. A0 is equal to 1. An works out to be a to the n divided by pi times the integral from 0 to 2 pi, 1 plus the cosine of 4 theta times the cosine of n theta d theta. Alright? And I can tell you, I already did this, and an works out to be 0 if n is different than 4, and a to the 4 if n is equal to 4. So basically that integral vanishes for all values of n, except when n is equal to 4. Because again, the cosine is orthogonal to the cosine. And 4 needs to, this needs to be cosine square, otherwise it will just vanish. And Bn happens to be a to the n 0 to 2 pi, 1 plus cosine of 4 theta, which is the boundary condition, times the sine of n theta, d theta. And here you can see again, the sine is orthogonal to the cosine, always. Independently whether n is equal to 4 or not, that integral will go to 0. Because the integral of the cosine times the sine is the sine squared over 2. Sine squared over 2 at 0 is 0, and the sine squared over 2 at 2 pi is also 0. So the only one, and the other one doesn't survive either, because the other one is the integral of the sine, which is the cosine, which also goes to 0, because the cosine of 0 is 1, and the cosine of 2 pi is 1. And those two cancel out. Okay? So Bn is equal to 0. So this turns out to be a simple solution, because notice, A0 is equal to 1. B0 is equal to 0. And all of the ANs are equal to 0 except 1, except when n is equal to 4. See? So, T of r and theta works out to be 1 plus a divided by r to the power of 4 times the cosine of 4 theta. So something that happens or started as this complicated looking series expansion ended up as a scalar type of solution, or not obviously a scalar, but solution that doesn't involve series expansion. Okay? And it does satisfy that, you can try it, this function right here satisfies the governing equation, the original governing equation, and it satisfies the boundary condition. This is the governing equation, you can make it, you can differentiate it with respect to r, with respect to theta twice, and so on and so forth, and you'll see that it's equal to 0. But you can also evaluate it at r equal to a, and notice that it will just satisfy directly this boundary condition. So this is typical of exterior problems. Most of the things vanish, depending on the boundary condition, obviously, but you can see how the solution actually goes away. As r goes to infinity, what's going to happen, see, is that the solution is going to tend to 1 everywhere. Because these terms right here will cancel out. Alright, so that's it. When we return next Tuesday, which will be our last class before the homework is due, we'll finish off cylindrical coordinate systems, and then when we get back from Thanksgiving, we'll just do a little review, talk about spherical, and then prepare for the test, okay? So have a nice weekend.
Do you want this? Yeah. Talk to him. Yeah. Oh, I see. Wait. Oh, so you'll have